So, in continuation with the last lecture, that is on modular arithmetic, in today's lecture we will be discussing about few things about the modular arithmetic. The very first concept is primitive root. So, what is primitive root? So, a number alpha is a primitive root of modulo n if every number co-prime to n is congruent to power of alpha modulo n. Quite complicated, not understanding. Let's make it simple. Alpha is said to be prime, a primitive root of prime number p. Okay, prime number p. If alpha to the power 1 mod p, alpha to the power 2 mod p, alpha to the power 3 mod p, up to p minus 1 mod p are distinct. Okay. So again, I am a little bit sure that, quite sure that no one has understood it. So what we will do, we will try to understand that with the example. If the question is, we need to find out whether 2 is a primitive root of prime number p. We are playing with the prime numbers, try to understand. And then we need to find out whether number 2 is a primitive root of prime number 5. So what we have to do? 5. So this 5 you have to consider as the number n, right? And the last stop number will be 4, right? Then this primitive number you need to take and you need to find out 2 to the power 1 mod p. P in the case is 5. 2 to the power 2, 2 to the power 3, and 2 to the power 4. You have to stop here because number is 5. So last power will be 4. And mod n. In this case, n is 5. N is 5. Right? And what you have to do, you need to compute the result of the same. Or is like all. Again, 2 to the power 1 will be 2 mod 5. 2 to the power 2 will be 4 mod 5. So you need to check, only check, very simple thing. You need to check whether all these numbers are distinct or not. Okay. That is the simpler thing you need to. So after having the modulus result to the 2 to the power 1 mod 5, 2 to the power 2 mod 5, 2 to the power 3 mod 5, and 2 to the power 4 mod 5, if we are getting the distinct result, like any number should not get repeated. 2 is repeated? No. 4 is repeated? No. 3 is repeated? No. 1 is repeated? No. In that case, we are saying that 2 is primitive root of prime number 5. Very simple. Taking the next example, we need to compute whether 3 is a primitive root of number 7. So same way, the last power will be 6 as the number is 7, right? And the 3 to the power 1 mod 7, 3 to the power 2 mod 7, 3 to the power 3 mod 7. You need to check the modulus result and you need to check whether any number is getting repeated. No, like not a single number is getting repeated. So in that case, you can say that 3 is a primitive root of prime number 7. Moving to the next example, if you want to check whether 2 is the primitive root of prime number 7, same way, the last part will be, okay, this is something which we have this, no. So last was 3. 3 was the primitive root of 7. Now we are checking whether 2 is a primitive root of prime number 7. So same procedure you need to repeat 2 to the power 1 mod 7, 2 to the power 2 mod 7, 2 to the power 3 mod 7, 2 to the power 4 mod 7, 2 to the power 5 mod 7, and you need to stop at 6 because the number is 7. And if you compute the result, you will get that 421 is getting repeated. So numbers result are not distinct. Every number is not distinct in the result set. So here we cannot say that 2 is a primitive root of 7. Okay, so no, 2 is not a primitive root of 7. So if the question is like this, right, you can solve this question at your own. You need to find out whether 2 is a primitive root of 11. Same process you need to do. And the next, moving on, if someone asks you what is the primitive root of number 5, so what we have to do? We have to again start with the number 1. We need to check up till 1 to the power 4. If we are getting distinct result, then we can say 1 is the primitive root of 5. If not, then we will move towards the next number. You have to check for number 2. If not, move to the next number. If not, move to the next number. That's how you can find out the primitive root of any number. Moving on, the next concept, that is the Chinese remainder theorem. Okay, CRT. So the way we are solving the equations, okay, we are having the x and y value if we are having the equations given, and with those equation, if someone asks you to calculate the x value or the y value, then you can solve that equation. In similar way, if we are having, so Chinese remainder theorem is used to solve set of different congruent equations. Like what we are discussing modular arithmetic. So here you will get the congruent equation, right? You will not get normal equation. So CRT will be useful into this case, okay? With one variable, but different modular, which are relatively prime as shown. So again, with the definition, it will not be clear to you, but I am quite sure that with the example, it will be more clear to you. If the equation is x is congruent to a1 mod m1, x is congruent to a2 mod m2, x is congruent to an mod mn. So what things are common over here? The x is the common, which is congruent to different equation, right? X is common and which is congruent to different equation, right? So if right hand side and right hand side is same, okay, so you can compute the x value, right? X value. So how? CRT will help you to come up with the x value, right? So now moving on. So how you can write this x, right? X you can write a1 m1 m inverse, a2 m2 m2 inverse, up to an mn mn inverse mod n. Now let's simplify it. The equation, if let's say we are having the equation like this, x is congruent to 2 mod 3. Second equation is x is congruent to 3 mod 5. And the third equation is x is congruent to 2 mod 7. 1, 2, and 3, right? X is common. Equations are different, like this. Right hand, left hand side is different, right? RHS is different, LHS is same. Then, so how the mapping is done? A1 and M1, A2 and M2, A3 and M3, right? So you can consider M1 as a 3, A1 as a 2, M2 as a 5, A2 as a 3, right? That way. And this is the Chinese remainder theorem ka equation, right? Now, this is equation. So these are the given thing, and we need to find out this. This is the equation of it. To have the x value, it's given by the CRT. A1 M1 M inverse plus A2 M2 M inverse, A3 that mod M will give you the x value. So just put the given value. We are having A1, A2, A3, and then we are having M1, M2, M3. Put the value accordingly, right? Once you put the value, and you will come to know that few things we need to compute and what we need to find out to put the value into equation, right? We need to find out m1, we need to find out m1 inverse, and then finally we need to find out this m. So how to do that, right? So according to Chinese remainder theorem, right, to find out this m, right, What we need to do, we need to do m1 into m2 into n3, right? This 3 is product. So m will be 105 in this case. Moving on, so m ka value we have inserted. And how one can have this m1 ka value? How one can have this m1 ka value? So it's nothing but m divided by m1. In similar way, m divided m2, m divided by m3, m divided by m3, right? It's an equation given. So putting the value into formula, you will be getting the value of m1, m2, m3. So this three values we are getting with the formula. Then next we need to compute this m1 inverse, m2 inverse and m3 inverse. This is something which we need to find out. So how to find out? This is nothing but the multiplicative inverse of m1 and m1 inverse, right? It's a 1 mod m1. Put the value. So you need to find out what is the multiplicative inverse of 35 mod 3. Okay, the result is 2. That's how you will be having m1 inverse as a 2. In same way, you need to find out the multiplicative inverse. m2 inverse will be 1. Multiplicative inverse of m3 will be 1. So again, the complete table is with us. Just put the value into the equation and then you will be getting the x value. So this is the Chinese remainder theorem with which you can solve the congruent equation. So this is another example which I thought you should solve, you should practice at home. That x is congruent to 8 mod 9, x is congruent to 3 mod 20. Moving on with the modular exponentiation, right? So with this modular exponentiation, so it is a type of exponentiation performed over a modulus, okay? So a to the power mod m, a to the power b mod m, or a to the power b mod m, okay? So if you are having 2 to the power 33 mod 30, 3 to the power 100 mod 29. So how to compute that? How to solve that? If the question is 23 to the power 3 mod 30, right? So how you can write this, okay? 30 is nothing but 23 and 7, right? 23 or and minus 7 or minus 7. So you need to remember this property of modular arithmetic, right? Below side we have written the number, right? And upper side we have written the result. And you observe that few modulus operator results are finite set of elements starting from 0 to n minus 1, right? So that when we are calling both the numbers are congruent to each other whenever their modulus results are congruent to each other. So 23 can be 23 or 7. 23 mod 30 is again congruent to minus 7 mod 30. Okay, so we can have either 23 or minus 7. Okay, we can have minus 7 to the power 3 mod 30, or we can write 23 mod 30. So what we will do, let's not go with the higher number, right? It's or, try to understand, it's or, right? It's or. So let's go with the smaller number. First one, minus 7 to the power 3 mod 30. So how minus 7 can be represented? Minus 7 will be represented minus 7 to the power 2 into 7. Like it is nothing but 1. So you know that, right? Into this kind of things, what we are doing, we are making this addition. 2 plus, when base are same, we are adding the power. So 2 and 1 will be 3. Minus 7 to the power 3 can be written like this, mod 30. And we know that minus 7 to the power 2 is 49. Minus 7 mod 30. Okay, that you need to calculate, and it will be giving you minus 133 mod 30, right? And again, you can have simplified it with the minus 13, and the final result you will be getting minus 13 mod 30 will be 17. So result of this will be 17. So what you have to do, you have to just simplify the things, right? Instead of just going with the looking at the bigger number, you need to find out the congruent factor of that number, which number is congruent to that number with that modulus operator. Okay, so to again visualize you, I'll take a minute and go to this slide so that it will be more clear to you. Otherwise you will, this is something you need to remember. Okay, in this case, if you observe, this is the modulus of 3, and modulus of 3 results are only 0, 1, 2, right? Irrespective of any number, the any number modulus 3 will be belongs to this set of result. You can have 2 to the power 19 mod 3. Result will be from this set. You can have any number 144 mod 3. Result will be from this set only. This is the modulus operator. So you need to find out again. So if result is finite set of element, of course there will be the number whose results will be equivalent. So in this case, this is of 3. In this case, which numbers modulus results are same? So for 0, number 3, number 3. For 1, you can have 1 result is 1. You can have minus 2, right? 1 mod 3 will be 1, minus 2 mod 3 will be 1. So you can replace 3 and minus 2 are congruent to each other for modulus 3. That is something which you need to understand, so that exponentiation can be easy for you. Okay, so 31 500 part to the 500 mod 30, you can 31. Okay, 31 can be replaced with the 1 to the power 500 mod 30. Both will be giving same result. Don't go with this power. 31 mod 30 will be 1, and 1 mod 30 will be also 1. So we can replace the 31 with the 1 because results are same. They are congruent to each other. And 1 to the power anything will be 1. Moving on, 249 to the power 329. So how, okay, same, right? It's a 241. Okay, so what we are getting? 240, forget about the power. 243. Mod 243. क्या आ रहा है? What we are getting? We are getting minus 1, right? So you can replace that with the minus 1. Or one can write, you can directly write minus 1 to the power 329, or you can write 328 into minus 1 to the power 1. And that's how you will be getting the result 243. So if anybody asks you to compute 11 to the power 7 mod 13, So how you are calculating it? 11 to the mod 13, you will be writing 7th time, right? 1, 2, 3, 4, 5, 6, 7. So the result you are getting minus 2 mod 13. It will be minus 128 mod 13, 11 mod 13. The result will be 2. Minus 28, 128 you have replaced with 11. So result you are getting 2. Or how you can do that? 11 to the power 7 mod 13, you can write like minus 2 to the power 7. Like 11 and minus 2 are congruent to each other for modulus 13. I hope it's clear to you. So now next topic is properties of modular arithmetic, which one should know. So A mod n plus B mod n whole mod n can be written as A plus B mod n. Then A mod n minus B mod n whole equation mod n can be written as A minus B mod n. In similar way, for multiplication, A mod n into B mod n, complete mod n can be written as A into mod n. So example, 15 mod 8 plus 11 mod 8, complete mod 8 can be written as, can be solved as 15 plus 11 mod 8. So that's how you will be getting 26 mod 8. The result you will be getting 2. So these are the properties of modular arithmetic. The very first property is commutative laws. So A plus B mod n can be written as B plus A mod n. A into B mod n can be written as B into A mod n. Associative law. So associative law, A plus B plus C mod n can be written as A plus B plus C mod n. Similar for the multiplication. Then it followed the distributive law. A into B plus C mod n can be written as A into B plus A into C mod n. Okay. Then identities. So in case of addition, 0 will be that identity element. So 0 plus A mod n will be A mod n. And in multiplication, the identity element is 1. So 1 into A mod n will be A mod n. Additive inverse, okay? So for each A belongs to Zn, there exists a minus A such that A plus minus A will be is congruent to 0 mod n, okay? So whenever this is used, we will throw the light on the same again. But I hope these laws are clear to you. Moving on, okay? So this is something I think we have, no, this is another example. So, okay, this is for the multiplication. The third rule is used over here to solve this equation. 15 mod 8 into 11 mod 8, complete mod n. But you need to remember that n should be common. Otherwise, in equation here 7 is there, here 6 is there, here again 7 is there, and you try to use this formula. It will not work. The n should be same, right? So in this case, what you have to do, 15 into 11 mod 8, 165 mod 8, the result will be 5. And moving on with the next property about group. So what is group? Group is denoted by G dot, okay? And this dot is nothing but a set of operations. This can be any operation, all right? It can be plus, it can be minus, it can be multiplication, any operation. And but when this is called as a group, when it satisfies the CAIN property. And what that CAIN property? Closure, associative, identity, inverse. Okay. Abelian group. So what do you mean by abelian group? A group is said to be abelian if it is a group. Okay. Group means what? It's follow the CAIN property. It's a group. And commutative property, you can see here the commutative property is not there. CAIN is closure, associative, identity, and inverse. So in addition to CAIN, it's also follow the commutative property, then it satisfy it will be also satisfied. What is that commutative property? A into B is equal to B into A for all A and B belongs to G. Okay, in that case we are calling, what is group? Group is just element, right? Numbers together separated by comma, and if these numbers are following, whatever numbers A and B numbers belongs to that group, if they are satisfying this associativity, closure, identity inverse and commutative property, then it is called as a abelian group, right? So we try to understand with this, the closure is this, right? When A and B belongs to G, then A dot B also belongs to G. Associative. So this is A into B into C will be equivalent to A into B into C. Okay. For all A, B, C belongs to G. Identity element. So there exists identity element. Then inverse element. Okay. Inverse element. And the commutative. So C, A, I, N, N will be called as a group. Along with this, if group is following commutative, that becomes the abelian group. So simple, right? So question may be like this, whether Z plus is a group. So what is Z? Numbers, right? So from 0, 1, 2, 3 positive and negative numbers. So you need to check, you can take any number as A and B from this set and you need to perform multiplication operation, right? And whatever result, if you are having, if that belong to G, then you can say that it's satisfy that property. So A here consider 5, B consider -2. The result A plus B or A into B, that is also belonging to J. So it satisfies the closure property. Then next we have check associative property. Any two numbers we selected from the group and we check with the formula. Again it is satisfying associative. There exists the identity element. For the multiplication you will be choosing identity element 1, and for the addition you will be choosing 0. If again the result is belongs to G, then you are saying that it's follow that property. Inverse, right? So 5 plus 5 minus 5 is 0. So that is inverse element and the commutative property. So if that group is following the satisfying this all property, then we are calling this as the abelian group. So we know the notation for different group. N is the set of natural number, W is the set of whole number, Z is the set of all integer, set of all complex number, set of all rational number, set of real number. Z plus is set of all positive number and Z minus is set of all negative number. Then the next is cyclic group. So when we are calling it as a G star, star is the operation. When we are calling it as a cyclic group, huh? So what are the element of G? 1 omega omega square. Okay. So you need to first have your composition table over star. Okay. So star is the operation and the element of G is 1 omega omega, and then we are having 1 omega omega. So the last element is omega square. Okay, so we cannot have the element beyond the omega square. The last highest element is omega square. So you can have 1 into 1 will be 1. 1 into omega will be omega. 1 into omega will be omega square will be omega square. In similar way, the omega into 1 will be omega. Omega into omega will be omega square, right? But you have written over 1 into omega square is omega square, right? Omega square. So omega into omega square. Okay, you cannot have, try to understand, omega into omega square, ideally it will be omega cube, but last highest element we are having is omega square. So when it's a, it will be 3, but omega 3 is not like it's not there into set, right? So what will be the result will be there, omega into omega square will be the highest element is that omega square. I hope you have, sorry, omega into omega square will be the 1. Okay, omega into omega. So again it is omega into omega square will be 1. So you need to, like, we need to start with the first element, right? Whenever we are having highest results, we will start with the first element. The way we are doing with the modulus operator, right? Then omega square into 1